All right, guys, welcome to your chemistry class. And today, what I'm going to do is I am going to review the section that was discussed today, which was section 2.1, the scientific method. So, what I'm going to do is kind of go over the concepts that we discussed in class and that you guys highlighted in your book for the benefit of those that might have missed something or uh, technology failed us. Well, this is a good resource, right? And it'll help us kind of get things back in order. Okay, so give me 1 second, guys. Apparently today technology is not cooperating. Okay, and we're back. I apologize for the inconvenience. Let's try that again. And hopefully now we will get the ball rolling. Yes. All right. We are rolling. All right, guys. So, pardon me for that. Section 2.1 actually starts talking about the scientific method. So, what I'm going to do is just read some of the concepts that we highlighted. And if there is anything that, worth writing that I think is relevant, I will go ahead and type it on the whiteboard. And the first thing that the book starts is to talk about or mention to us the scientific method. And the definition, according to your book, says the scientific method is a logical approach to solving problems by observing and collecting data, formulating hypotheses, testing hypotheses, and formulating theories that are supported by data. So, one very important thing about the scientific method is that it has to be supported by data. So, let me just write real quick what the characteristics of the scientific method or what it's supposed to be. First of all, it's supposed to be a logical approach. So, it has to make sense, right? Or at least make sense into what you want to talk about. The second thing is that it involves observing and collecting data. So the first step, I guess, you want it is observation. After the observation, I um, generate or formulate a hypothesis. Then I test that hypothesis or experiment. And finally, I formulate theories. And we're going to get into all these concepts in just a minute. So that's pretty much, you can say the steps in the scientific method don't vary. What varies maybe is what they're called. Okay, like for example, some book might say instead of testing hypotheses, experiment, but it's the same thing, right? And we go on in your book and it says observing is the use of the senses to obtain information. So when we observe, we use our senses to obtain information. When we observe, we use our senses to obtain information. Okay, senses like our five senses, something that'll help us obtain our information and then analyze that information to understand it. And of course, the two types of information that we have are numerical information or quantitative information. An example of that could be a sample of copper A has a mass of 25.7 grams. Okay, that's an example of numerical data. And non-numerical data or qualitative data is, for example, the sky is blue. So that's an example of what numerical data is. And It says experimenting involves carrying out a procedure under controlled conditions to make observations and collect data. So, one very important thing about an experiment is that an experiment occurs under controlled conditions. Why is that? It's because in nature, it's pretty hard. It would be pretty hard to study a particular phenomena if, if you didn't have controlled experiments. Okay. And when we start talking about models and model making in a minute, we'll see how important that is. Okay. So, again, experiments occur under controlled conditions. Okay. And it says that to learn more about certain phenomenons, um, or matter in the case of chemistry, chemists study systems. And what is a system? It says a system is a specific portion of matter in a given region of space that has been selected for studying during an experiment or observation. So a system is something in particular or a portion of the matter. It's not the whole phenomenon, because again, the whole phenomena has a lot of variables. And if I'm working with an experiment, remember that I said that an experiment has to be in a controlled environment. Hence, that's why we use system or a portion, or chemists use a system or a portion of matter that they want to study. Okay. So all these concepts are highlighted in your book, specifically on page, I believe this is page 27. Okay. And now we're going to talk a little bit about hypotheses. So, a hypothesis can be defined in many, 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 many ways. The most common form of defining a hypothesis is people call a hypothesis an educated guess. So, we can say that a hypothesis is an educated guess, but there's more to that. Okay, and we're gonna talk about that in a minute. And in on page 28 of your textbook, it says, as scientists examine and compare the data from their experiments, they attempt to find the relationship and patterns. In other words, they make generalizations based on the data. Now, this is what we highlighted. It says, so scientists make generalizations. Even though we're studying a specific phenomenon, they make generalizations. When you make or form a hypothesis, is a generalization. It's something that you think that is going to apply to everything. Of course, it is through the experimentation that we know if in fact the hypothesis is true or not. So, what we highlighted in today's class is that generalizations are a statement that apply to a range of information. Okay, so generalizations, and let me see if I can write that down. I think here would be better. It says generalizations apply to a wide range of information. Of information. Okay? Um, for example, birds fly, right? My hypothesis is that all birds fly. Well, if that's true, that applies to all birds. And of course, we know that that's not necessarily true. So that's why hypotheses are a general statement. They're a generalization. And again, a generalization is statements that apply to a wide range of information. It goes on to say that to make generalizations, data are sometimes organized in table, in pie charts, um, or using statistics. Okay, so that's pretty important. And it's just to make generalizations. Data is sometimes organized in tables or graphs. And that's very important in experimentation. Tables and graphs are very important because they help scientists come up with the conclusions that they need to know if the hypothesis is true or not. So I'm actually going to go ahead and clear my drawings. Again, those highlights are in your those statements are should be highlighted in your book, or if not, you can always pause and rewind the video. Right. Um, so now let's define the hypotheses. Okay. So according to your textbooks, hypotheses. Can be defined or is according to your textbooks, hypotheses is a general. It says scientists use generalizations about the data to formulate a hypothesis or a testable statement. So the hypothesis serves as a basis for making predictions and for carrying out further experimentations. So first of all, hypotheses must be testable. Okay, if I cannot test the hypotheses, then I need to reformulate it. Okay. Also, is that the hypothesis serves as the basis for making prediction, and we go back to what we were saying. It's an educated guess. Okay. The other statement that we highlighted in the book actually talks to us about uh, control and variables. Now, whenever we scientists conduct an experiment, you have a control group. And let me read what we marked today in the book, and then I'll go a little bit more in depth into that. It says, during testing, the experimental conditions that remain constant are called controls, and any condition that changes is called a variable. So a variable is what changes. A control group, if we talk about science, we have a control group. That's the group that really isn't really exposed to the variable that I want to test. Whereas the variable is that which changes. So if we talk about, for example, testing a vaccine, the control group would be the group of patients. If we're talking about clinical trials, the control group is the group that is not affected, or who, in this case, in which the vaccine is not tested on, and the variable is the group that is tested, and that's the group that changes. Okay, so that's also very important. Um, it says any changes observed is usually due to the effects of the variable. If testing reveals that the predictions were not correct, the hypotheses on which the predictions were based must be discarded or modified. So, in other words, what that's saying is that the experiment, if the experiment does not prove the hypotheses, then the hypotheses must be discarded or modified. Generally, scientists don't like to say that the hypothesis is not true. Generally, what they'll say is that the hypothesis needs to be modified, or that further testing is needed to prove the hypothesis. But it's very important to understand that the experiment is what's going to test my hypothesis. Is what's going to tell me if it's true or not true. And if it isn't true, then I have to modify it. And we're going to go to the last page of this section where it talks about models. And it says models, ideas that help or helps to form theories. And it goes on to define what a model is. And a model in science is more than a physical object. It is often an explanation of how phenomena occur and how data or events are related. It says models may be visual, verbal, or mathematical. So basically, what a model is an explanation to a phenomenon. And in class, I actually gave you guys an example of that. So a model is what's used to describe a phenomenon. First of all, whenever we are working with a model, we have to assume that other variables are not existent, not because they're not there, but because what happens is that if I include them in the phenomenon that I want to study, it's going to make it a lot more complicated. And one of the phenomena that I was talking to you guys about is gravity. So we all know that in Earth, gravity pulls us downward, right? And sometimes you might ask yourself, well, yeah, but why don't I sink if gravity pulls me downward? And I was explaining that's because as gravity pulls you downward, there is another force that has to push upward with the same amount of force. So if I want to study this phenomenon, I need to eliminate all other variables that could possibly be present. Why is that? Is because a model needs to be simple in order to explain a phenomenon. So once again, that is page 29, and the definition of a model on page 29 is that in science, it says a model, in science is more than a physical object. It is often an explanation of how phenomena occur and how data or events are related. Okay? Models may be visual, like the example that I just did there. They may be mathematical, such as E equals mc squared, for example. That's an example of a mathematical model. Or in algebra, y equals mx plus b. And it goes on to say in the paragraph that one important model in chemistry that we're going to study is the atomic model. And the atomic model suggests that all particles, or that matter, is composed of tiny particles called atoms. So that's an example of a model that we're going to study a little bit later on. It says, if a model successfully explains many phenomena, it may become part of a theory. So if a model explains a lot of different things, then it can become a theory. And to summarize a theory in very simple terms, although I'm going to read the definition in about a minute, a theory is something that explains a wide array of, in this case, natural phenomenons. Okay? So it's just a hypothesis is an educated guess to a specific problem. A theory is probably, I don't want to say an educated guess, but it does help give a general explanation of more than one possible phenomenon. Okay. Now, according to your textbooks, and I'm going to quote your textbook in a minute, it says that a theory is a broad generalization that explains a body of facts or phenomena. So again, a theory is still a generalization, but it is a broad generalization. And by broad generalization, what I mean is that it explains many phenomena. Okay? So that's what we call a theory. And it goes on to say that theories are considered successful if they can predict the results of many new experiments. So just like the theory of relativity, if that is going to be, when the theory of relativity was considered a theory, it was successful because it predicted the results of other phenomena that was related to what Einstein wanted to study at that point. Okay. And it says that examples of important theories you will study in chemistry are kinetic molecular theory and collision theory. All right. So, guys, that is it for this class on the scientific method. I hope that this video is helpful, and we will see each other in our next class. So stay safe.